When last we left off, we were talking about the number systems. In particular, we covered the decimal system, which we use every day, and the binary system, which is used by computers because of the two states that it can be in, 0 or 1. Today we're going to talk about hexadecimal. Which is base 16. Like I said before, the number of the base is the determiner of how many symbols are used. So base 16 has 16 symbols used to represent numbers. We use the 10 decimal symbols for the first 10 symbols of base 16, and then the remaining 6 are A, B, C, D, E, and F, representing 10, 11, 12, 13, 14, and 15, respectively. As with any base, any number system, the position determines the value of the number. So the different positions have the different values. The base raised to the increasing number power as you go left, starting at 0. So this is the 1's position. This is the 16's position. 16 squared. What is 16 squared? Anybody have a calculator handy? Is it 256? Yeah. 256, yeah. The 256's position, and multiply that by 16 for the power of 3. Is it, huh? That's the 1's, 2's, or 1's, 16's, and 256's. Yeah, that's an S, not a 5. What's 16 to the third power? 4096. Okay, so this is the 4096 position. So a 1 here means 4096. A 2 here would mean 512. A 4 here would mean 64. So let's look at that. Say you have the hexadecimal number 1, 2, 4, D, base 16. So that's 4096 plus 512 plus 64 plus D is 13. Uh, 46, 72, 46, 85. So it'd be 46, 85. Is that right? Somebody with a calculator check my math? Base 10. Is that right? Somebody have a calculator handy? It is right? Oh, okay. Miracles do happen. So that's how you would convert a 4-digit hexadecimal number into decimal. Likewise, if you wanted to convert, let's do something a little bit smaller here. 132 base 10 into hexadecimal. Well, you got your powers over here, 256, 16, and 1. So no 256s will go into 132. How many 16s will go into 132? 8? Is that right? Oh, okay. So you'd write an 8 over here. And 8 times 16 is 128, right? 128. Take 128 from 132, gives you 4. Put the 4 in the 1's position, and that's your number in base 16. If somebody has a fancy calculator with with number conversions on it, you can check my math on that. But you can represent much larger numbers with fewer digits using hexadecimal. That's why it is used in programming and such, because a 64-bit number, like what you would have in the computer for addressing a memory, 64. Most computers are 64-bit nowadays. That means they can address, have memory addresses up to 64 bits. Divided by 4 is 16, so that would be 16 hexadecimal digits instead of 64 binary digits. So it's considerably less digits used to represent large numbers. And you might ask how I came upon that number 16. Well, hexadecimal, let's go ahead and write this out here. 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, and F. Now those correspond to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15 in decimal. And this is hex. The nice thing about hexadecimal is it corresponds to one group of 4 bits, or a nibble, half of a byte. So those are in binary. It's a 1-to-1 correspondence between each combination of 4 bits that you can have to a hexadecimal digit. So you see a hex digit, all you have to do is remember this chart. Or if you're working on a quiz or something like that that requires the conversions, just write it out on the side so you can reference it. It's real simple. Count up all combinations of 4 bits in order, and then have the hex number digits beside each one. So you have a hex digit here, or hex number here. Convert it easily to binary. 3 is 0, 0, 1, 1. C is 1, 1, 0, 0. D is 1, 1, 0, 1. And 4 is 0, 1, 0, 0. It is simple as that. Likewise, if you have a binary digit, a binary number, say 1, 0, 1, 1, 1, 0, 1, you might say, wait a minute, that's only 7 bits. You can add leading zeros to it to make it a complete nibble. 101 is 5. Come on. And 1101 is D. Simple substitution. No real math involved. So if you find converting a number from decimal to binary easier than decimal to hexadecimal, which I personally do, you can convert it to binary and then do the simple substitution and get the hexadecimal. Again, it's just simple substitution. So I strongly recommend writing this chart down so you can have that as a reference for quizzes and tests and future classes. Now, if you recall, we did negative numbers in binary, which we can do in hexadecimal as well. The same process. So say negative 37. First convert it to binary. So you have 32s, 16s, 8, 4, 2, and 1s. Ignore the minus sign for right now. 32 will go into 37. So you put 1 there. Leaves you with 5. No 16s. No 8s. But a 4 will go in there. Leave you with 1, so no 2s, but there's a 1. Now you convert it to a negative number using 2's complement, which we learned last time. So 2's complement requires groups of 4. So add leading zeros here to make a group of 4. Group of 4. Invert the bits. And then add 1. So you have the 8-bit 2's complement. So this is negative 37 in binary. And then you just do the simple substitution from binary to hexadecimal. So that's, what is that, 11, which is B, 13, which is D, right? Yeah. So this is dB in hexadecimal equals minus 37 in decimal. Notice there's no negative sign out front. It is a 8-bit 2's complement representation of negative 37 in hexadecimal. And likewise, you can take a negative number in hexadecimal. It's a 9C. Convert it to binary first. 1001. And C is 1100, right? Then you invert the bits. Then you add 1. Okay? So that's the magnitude of the negative number. Because it had a 1 in front at the beginning at the conversion from hexadecimal to binary, it's a negative number, but this is the magnitude of it. So you convert this from binary to decimal, which is a 4, no 8s, no 16s, a 32, and a 64, which is 96, 100. So it's minus 100. People rarely do math and other manipulations directly with hexadecimal. It's easier to convert to binary, do the math then, and then convert it back to hexadecimal. Yeah. Oh, no, it's 64 plus 32 and plus 4. This is the 1 in the 4's position, none in the 8s, none in the 16s, 1 in the 32, and 1 in the 64's position. Yeah. But you take the hex number, convert it to binary, and then convert the binary to the decimal value. Just a lot easier than trying to do 2's complement on hexadecimal, which I'm not aware of any system that is remotely simple to do. This is much easier. Is everybody following this, or need another example? Yeah, yes, no?
I would appreciate one.
One more example, okay, of going from hexadecimal to, let's say, C5 hexadecimal will be what, 1100 and 0101 in binary. Get rid of that. Now do the 2's complement conversion. Go 0, 0, 1, 1, 1, 0, 1, 0. Add 1. 1, 1, 0, 1, 1, 1, 0, 0. Then convert this to decimal, which is a 1, a 2, no 4's, there's an 8, there's a 16, and a 32. So that would be 59. Because the leading 1, it was a negative number, so you hold that and the sign over here, and then determine the magnitude of the negative here, 32, 16, 18, 2, and 1. No, that's not right. No, that is right. 59, yeah. Minus 59. If my basic addition is correct.
I'm just figuring out is like why when you right to left, you got 1, 1, 0, 0. That's 1, 0, 1. Like what's happening there?
Where do you mean? From here to here?
There is. I was going from right to left, but yeah, that was it's there too.
The first step of 2's complement conversion is to invert the bits.
Right.
So 1, 0.
Well, the adding part of it.
Oh, you add 1 to it. So you add 1 to the. You're done with this. You're done with this. You're adding 1 to this number here.
Oh.
1 plus 0 is 1. 1 plus 0 is 1. 0 plus 0 is 0. So on and so forth. Mm-hmm. But well, if there's any other questions, we can call it a day. Remember that essay assignment due at midterm? No, it doesn't count as it does not count as your midterm. There is going to be a midterm exam. It's just due at midterm, so I have time to grade them before the end of the semester. So have a good day. See me